Now let's resume. Let's move on to applications on harmonic oscillation. Okay, how about this kind of example? This is kind of like C1 cosine of omega t plus C2 sine of omega t, and somehow you have to combine them into one trigonometric function, a sine of omega t plus v. And in this case, a is called the amplitude, omega is called the angular velocity, and v is called the phase shift. And it is quite typical that solutions of a differential equation come out kind of like this. C1 cosine plus C2 sine, and somehow you have to combine those into a single sinusoid. How do you do that? Well, you have to use the sum identity, of course, but you have to start from the backward. And the sum identity for sine is built kind of like this. Sine of alpha plus beta is equal to something like that. So if you know alpha plus beta, you can get that one, but going backward is difficult. So it's usually not a good idea to start from here. Better to start from there. Okay, and let's apply the sum identity. Sine of alpha times cosine of beta plus cosine of alpha times sine of beta. And let's break out the parentheses and do some juggling. Then what do you get? A cosine of phi times sine of omega t, and a sine of phi times cosine of omega t. Let's combine that, and let's compare that with the first form, left hand side, 3 cosine of 2t plus 4 sine of 2t. Which is which? Cosine of 2t will be cosine of omega t. So omega is 2, and 3 will be this a sine of phi. Now sine of omega t and sine of 2t, so they match, so omega is 2, and a cosine of phi will be 4. You see, you can find out those coefficients by comparing them. Consequently, we have the system of equations. A cosine of phi is equal to 3, and a sine of phi is equal to 4. Now we have two unknowns and two equations. Looks like this is okay, but there's a big problem. This is not a linear equation, so you have to use some trick, some unusual trick. Some unusual trick, but not outrageous. Here in the trigonometry, we have to use something related to trigonometry, and the most important equation in trigonometry is what? Pythagorean identity. Cosine squared plus sine squared is equal to 1. And we have cosine and sine, so you have to have that kind of thing in the back of your mind somewhere. This is very, very typical trick. So what we have, a squared is equal to a squared cosine cosine squared, and a squared sine squared. Excuse me, there's a typo. So square that. A squared cosine squared is 3 squared. Square that, a squared sine squared is 4 squared. And then cosine squared plus sine squared is equal to 1, so we have just a squared there. Or maybe let me make it a little bit more explicit this way. So cosine squared plus sine squared is equal to 1, so this is equal to a squared. And then, well, okay, that, and then cosine a squared cosine squared is actually 3 squared. A squared sine squared is 4 squared. 3 squared plus 4 squared is 25. Taking the square root, we get a equals to 5. In general, you're going to get a lot more complicated number, but that should be just a number. In general, you're going to get not just nice 3, 4, 5 triangle, but some number here, some more complicated number there, and this will be the sum of those squares of those numbers, and this will be the square root of the final number. So it's far more complicated in terms of, well, computation, but theoretically it's the same deal, as a matter of fact. Anyway, now that we have A and then A value identified, you can find a phi by cosine of phi is 3/5, because plugging A value equal to 5 right over here, we get A cosine of phi, or 5 cosine of phi is 3, so cosine of phi is 3/5. We get cosine of, you get phi as arc cosine of 3/5. Or equivalently, you can plug it over here. 5 sine of phi is 4, so that phi is arc sine of 4/5. They're going to be the same deal. I decided to use arc cosine, but it doesn't matter if you use arc sine. Maybe. I'll just put it over there as well. It's the same deal, because arc cosine of 3/5 or arc sine of 4/5 should be the same. Tricky, yes, and am I going to write this kind of problem in the exam, for example? I must say it's unlikely. You see, if this were a big university with an engineering program and most of the students sitting in this classroom or taking my courses are just the same major, and then that happens to be something related to electrical engineering, then of course I'm going to select this kind of problem and a whole lot of other applications in electrical engineering and do that. But here in UNT Dallas, we have very small class with diverse majors, so if I concentrate too much upon one application, I may end up alienating other kind of students. So usually I do not overemphasize applications. Usually, not always. So keep those in your mind. It's a nice example, yes, but do not overemphasize. Okay, we have some time left, so let's talk about some geometry problems, and some of them are gonna be hard. How about this problem? In triangle ABC, the line segment S bisects an angle C, as you can see on top. Show that the length of the line segment is, there, 2ab cosine of x over a plus b. Well, 2ab cosine of x, that looks like coming from the law of cosines. Well, will that help? I don't know. I mean, I know the answer. Yeah, I mean, I take you back. I know the answer, but I better not really tell you that. Geometry problems tend to have the key step right up front. Actually, the very first step tends to be the most important step. So if I just give away the first step, that's I end up giving away everything. So I'll try not to do that. Okay, let's move on to the second problem. Find the dimension of the inscribed rectangle with the largest possible area. This one I can give you a little bit more. Let's see. How do you express the area of this rectangle in terms of angle theta? Because you see, we're going to find out theta, so it has to be written in terms of theta. So this is what we are going to do. Area is width times height. And what is width in this case? Well, we have the angle theta and the radius is 5. So the width here in this case is 5 cosine of theta. I hope you can see that. The width is 5 cosine of theta. 5 is the radius, hypotenuse. Actually, no, excuse me. It's not 5 cosine of theta. Excuse me, it's 10 cosine of theta. As a matter of fact, 5 cosine of theta times 2, excuse me, because that's 5 cosine of theta will be just adjacent of this triangle, and that's going to be just half of this width of this rectangle. Now, how about the height? It's going to be 5 sine of theta, because height is the opposite of this angle and the hypotenuse is 5. So what we get, 5 times 5 times 2, 50 cosine sine of theta times cosine of theta. That is your area. Now, please recognize that we are doing double angle formula here in this set, and we have sine of theta times cosine of theta. So my suggestion is to use the double angle formula here. What is the double angle formula? Here it is. Sine of 2 theta is equal to 2 sine of theta times cosine of theta. So what do we get? We have 25 sine of 2 theta. And that is the area expressed in terms of theta. Why will this help? Well, my question here is, when does the sine function reach the maximum? Sine function reach the maximum at theta. The angle is, okay, I'll stop here. About 4.4a. Okay, let me give you one little hint. Think about the area of the triangle ACB using the trigonometry. That is my hint. Think about the area using the angle C and also using the angle X. There are two triangles with the angle X. And if you add up the areas of those two little never mind, I'm giving away too much. I'll stop here.